Alright, so this is the first video of many for me going over the homework assignments within my class at South Dakota School of Mines and Technology. If you're on the interwebs, you're more than welcome to watch, but I am going to be kind of specific to my own class. So, for those of you in my class at least, this is the first homework. First problem. This is on Maxwell's relationships in general. And the problem says derive dA equals minus S dt minus P dV. And so we derived this in class. What did we use to derive? Well, we didn't derive this one, we derived this one. Let's see, TdS plus VdP. Okay, so we derived dH equals TdS plus VdP. How did we derive that in class? What, on our calculus cheat sheet, what did we use? Well, that's right. We used the total differential. And the total differential states, if I look at my cheat sheet, it says, in general, dF equals dF dx at constant y times dx plus dF dy at constant x dy, where f is a function of both x and y. Okay? So in this case, we have our dA is our f, and our x and y are what? They are t and v. The reason why they're t and v is because of where we got this. A came from the transformation, using the Legendre transform, the transformation of s to t. So s became t, so u was a function of s and v. Well, we left v alone, and then we transformed t. So a is a function of t and v. And so those are our x and y in this case. Okay, so f is going to be a, and so this is going to look like dA equals dA dt at constant v dt plus dA dV at constant t dV. All right. Now, normally, when we see a dA, what should we do? That's right, we should plug it in. But we're trying to derive the thing that we would plug in, so we have to plug in what A equals. And right here, we have A equals U minus TS. Okay, so let's do that. So we got two here. We got dA dt at constant v and dA dV at constant t. Okay, so let's do this first one first. Okay, so let's, and throughout all of these problems, you're going to see lots of erasing because I don't have that big of a chalkboard. All right, so we've got dA dt at constant v. And we want to plug in what A equals. So we have du minus TS dt at constant v. You might be like, well, can we do that? I mean, dA dt, that's a derivative, right? Well, we have to remember our numeracy. dA dt at constant v is not a derivative. It's a relationship. dA is not some esoteric, weird calculus construct. It's how A changes. And how A changes is the same way as how U minus TS changes. Okay. Think of it as how much money I have in my bank account changes the same amount whether I'm in quarters or in $50 bills. If I take out $50, it doesn't matter if it's in the form of quarters or if it's in the form of dollars, I'm still going to be taking out $50. Okay. So we've got this, but But because this is calculus, I can use the same kind of calculus rules. And just like when I'm taking the derivative of, let's say I'm taking the derivative of y equals x squared plus natural log of x, okay? Well, I can take the derivative of each one separately and add them together because they're additive. Same thing here, okay? So I can break this up into its addition. So I can say du dt at constant v minus dts dt at constant v. Okay. But what do I do about that ts? Now remember what we did in class. So what calculus rule did we do in class? That's right, we used the product rule. We can't just, say it's, okay, t ds, whatever. Okay, we have to do the product rule. Okay, so let's do that. We'll come back to that guy. We'll remember him. Okay. So let's break this up using the product rule. Okay. So minus t ds dt at constant v minus s dt dt at constant v. All right. Do we know what ds dt at constant v is yet? No, I mean, at the point where we derived the dh one, did we know? No. Okay. So we're just going to leave that. Okay, dt divided by dt. Now, because this is a change in temperature, the change in $50 in bills and the change in $50 in quarters is still equivalent. So 50 divided by 50 is 1. All right. Okay. Now, what do I do with this du? Well, I plug in. Now that's where I can plug it in. Okay, everything, plug it in. Okay, so du equals tds minus pdvx. One you should just have memorized. Okay, so we can plug that in. So t ds dt at constant v minus p dv dt at constant v. All right, I've got t ds dt at constant v. Do I know what ds dt at constant v is? No. But hey, it looks exactly like that guy, but a different sign. They cancel each other out. Okay? Now dv dt at constant v. Now what does dv mean? It means a change. What does constant v mean? It means it's constant. So what happens when you try to change something that's constant? Nothing, aka it is equal to 0. So those cancel out. That's equal to 0, that's equal to 1, and I am left with minus s equals dA dt at constant v. Okay? So there's that half, and then I have the other half, which is dA dV at constant t. This is still the same. Still plug in A. This is a V and this is a D. Still separate them. I still do a product rule, but of course the thing that's different here. Let's try and preserve that as much as we can, but probably not too much. Okay, so dV dt minus s dt dv at constant t. Okay, ds dv at constant t. Do we know what that is? Don't know what that is. Okay, dt dv at constant t. What's that? Same thing before. That's 0. Okay, and then this part. It's the same thing in terms of plugging it in, but this time I have dv at constant t. So I have t ds dv at constant t minus p dv dv at constant t. Oh, that's 1. Oh, that doesn't mean anything, but t ds dv at constant t minus t ds dv at constant t. Ah, those are the same. That's 1. And I have dA dV at constant t is equal to minus p. Okay, so going back to our original total differential. It said that df is equal to df dx at constant y dx plus df dy at constant x dy. Okay. Well, our f is a. Our df, our x is t, and our dA dt at constant v, y is v, is minus s. Our x is t. This was minus p dv. Oh hey, that's our answer. Ha 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 ha. And that's all there is.